All right, why don't we get started? So let me start by recapping what we talked about last time on Hurwitz's theory. We introduced the notion of moduli spaces, right? These are geometric objects whose points parameterize your favorite geometric objects, so they're in a sense sort of meta geometric objects. It's especially cool when they have what are called universal objects, which means that if you have a modular space of Mickey Mouses, right? Every point in your space is a Mickey Mouse, but there should be a house of Mickey Mouses with a function down to your space such that the inverse image of each Mickey Mouse is exactly the Mickey Mouse that the point corresponds to. Okay? And also, you can do moduli theory from many, many different perspectives, from very abstract ones to very concrete ones. But a very useful way to actually then compute and do geometry on moduli spaces is to exploit stratification that they often have, or that we rig so that they have. And this stratification means that these moduli spaces have a big open set that corresponds to sort of like exactly the objects that you love the most, and then you allow them to become progressively more degenerate. So for example, you might really love smooth curves, but then you might allow them, in order to have compact spaces, to have nodes. Right? And then the more nodes curves have, the more you think of them as being degenerate. Right? And so by doing so, you get actually a stratification by progressively larger codimension strata. And then often what you get is that the strata themselves can be described as products of quotients of products of quotients of other moduli spaces with simpler invariants, which give you access to sort of combinatorial/recursive techniques. Okay? The examples that we've looked at yesterday were, the moduli space M0n of equivalence classes of n tuple of distinct points on P1, where the equivalence is given by moving all the points around simultaneously with automorphism of P1. And then we said there's a couple ways that people know and love how to compactify such a space. One is to never allow points to coincide, but to allow the curves to become, instead of just a single P1, become nodal curves. Okay? And this is called the M0n bar, the Lin-Mumford moduli space of stable curves. Right? Or you can be a little bit less committal, and you can say, well, let me attach a weight, like a rational number, a real number between 0 and 1 to every point. And then when points want to come together, you add their weight. And if they don't surpass a critical mass, then you just let them coincide. And if they do surpass a critical mass, then you act as if you were an M0n bar, which means that you create a new bubble and you transfer the points on this other bubble. Okay? And these are two nice, smooth, projective compactifications of M0. From the point of view of Hurwitz numbers, right, we like moduli spaces of covers, right? So the Hurwitz space is our space of non-degenerate objects, parameterizing smooth covers from smooth Riemann surfaces to, and let me just, again, do the P1 case for simplicity of indexing and things to write. So smooth covers from curves of genus G to P1 with fixed discrete invariants, but where the position of the branch points is not fixed. Okay? And again, this has two compactification, and admissible cover compactifications where basically you never allow branch points to come together. If they want to, you put them on a different universe. And a rubber relative stable maps compactification where you separate your branch points between some that cannot come together and some other that can. Okay? And why? Well, hopefully between my course and Dhruv's course, and I think this will not play a huge role in Hannah's course, but you'll see some reason why you might. What are the features of the two in these things? But then what happens is that there's a natural morphism between the spaces, because given a Hurwitz cover, like a cover, you can just forget the top part and just look at the branch points. So you get a natural branch morphism from the Hurwitz space to M0n, and then the Hurwitz number is simply the degree of this morphism. Because what does it mean to compute the degree? It's like fix a point in the target and look at the inverse images, but fixing a point in the target means fix the position of the branch points. And so the number of covers that have those branch points is exactly how we define the Hurwitz numbers. And those automorphism factors, they all come along for a ride because we really want to think of these as stacks, and so points are really points, mod groups, and yada, yada, yada. Okay? And then the key thing is that this branch morphism, well, this thing is lovely, but it's uncomputable at this level. And so we want to compactify and try to compute it via intersection theory. Right? So this branch morphisms kind of extend in both of these worlds. And now this is a proper morphism, right? And so you can actually say, well, let me take and express this as the degree of the pullback of the class of a point, and you can unleash techniques to do that. Okay? One thing that I shoved under the rug very happily, but let me, since I got caught, let me mention it real quick, because I also want to draw a picture that I think it's nice, right? So if we start with my branch morphism, right? From the Hurwitz space to M0n, it's a nice, good cover, and really the degree is like you take a point and you look at the number of inverse images, right? Oops. Right here. Okay. And then when you compactify, like the compactification by ADM, it's sort of a smooth compactification. So from a geometric point of view, this is really kind of a nice picture, because really, like, we have the branch upper star of the class of point, which is what it is, right? But when you compactify with relative stable maps, then what you end up doing is that you might actually have excess dimensional components in your moduli space. Okay, and so what degree really means is a little bit more worrisome, but that's when we remember that we had a wonderful lecture yesterday by Francesca about saying when something is wrong dimensional, call up somebody like her, and she's going to chop it down, whittle it down with virtual techniques, right, to something of the right dimension, so you can still make sense of saying what is the pullback of the class of a point, right? And in this case, there's also this kind of advantage that all the crap that happens in this compactification, it doesn't map dominantly on the target space. So really, even though you have to ask Francesca to set up virtual things to do things honestly, the answer is going to be always the same. Okay, so this is why this picture is, the statement I made yesterday was honest, even though not fully complete. Okay? Any questions so far?
So buried in there is the statement that actually the virtual degree is equal to a naive degree.
Yes, that's what I was trying to say in the last minute. Yeah, exactly. Which depends on the fact that this excess dimensional components, these boundary components that you need to really cut down the virtual fundamental class, they don't map dominantly down here, and so that means that they get missed. Cool. Any other questions or comments? No? Yeah.
Why is that enough?
What?
Why is that enough? Maybe I should ask.
Let's talk about it later. Yeah. All right. Okay. So from this perspective, you get ways to connect Hurwitz numbers to the geometry of the moduli space of curves, right? And in fact, I believe on Monday, Vance is going to tell you about the ELSV formula, right? This is a remarkable application where you will see that single Hurwitz numbers, so Hurwitz numbers always have exactly one special branch point. So exactly one, this vector of etas is just one eta, right? This single Hurwitz numbers can be expressed as an intersection number of tautological classes of MGN bar. This is a fantastic formula because it really connects, something which is very sort of combinatorial and algebraic, such as the Hurwitz numbers, to something deeply geometric, which is the tautological intersection theory of MGN bar. Okay, so look forward to Vance's lecture Monday. Today, I wanna get directly to the thing that touches base with the tropical world a little bit more naturally. So we're going to introduce tropical Hurwitz numbers, but before I do that, I need to introduce another sort of special family of Hurwitz numbers, right? So double Hurwitz numbers. Right? And so double Hurwitz numbers, again, the picture is the base is P1. I have only 2 points that if I want, I can choose to be 0 and infinity, where I can specify special branching, and all the other points I fix, I have simple ramification. Let me call it tau, 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 tau. Right, so the picture, maybe to have in mind, is something like this, right, where I control ramification on a couple of over 0 and infinity, and everywhere else it has to be generic. Okay, so these are, in our notation, would be h g to 0 of degree d, some r, and then I have eta 1 comma eta 2. Okay, and when we deal with double Hurwitz numbers, since we're always in that situation, we drop a bunch of redundant invariants, so we often just call these hg vector x, right? And what has happened here is that, okay, first of all, we drop the 0 because it's all, if we're talking about double Hurwitz numbers, the base is always going to be P1. We drop the r because r is going to be 2g minus 3 plus n. I haven't told you what n is, but I'll tell you in a second. And we kind of absorb the 2 partitions of d, eta 1 and eta 2 into just one vector, x, where I say, okay, what I'm going to do, right, if I have eta 1, let me just, instead of saying something confusing, let me do one example. If eta 1 is 5, 3, and eta 2 is 6, 1, 1, right, then what I'm going to do, I'm going to flip the sign in front of one of the 2 partitions, and I'm going to give you a vector of numbers that add up to 0. This is my x. Okay. And in a second, I'll hopefully motivate why that's sort of not something that we can do, but something that's actually interesting to do. Okay? Cool. Any questions on notation so far? Or the definition of double Hurwitz numbers? Yeah, Matt.
So, like, eta 1 and eta 2, like, the orders doesn't matter. So x has an ordering?
Yeah. I mean, if I'm choosing eta 1 to be the point 0 and eta 2 to be infinity, then, by convention, I'll have the eta 1 be positive and the eta 2 be negative, so that really I can think of this as the divisor of the rational function corresponding to this cover, right? Of course, if you flip all the signs and you ask what is the Hurwitz number, it's going to be the same Hurwitz number, right? So there is this kind of invariance. Yeah. Cool. Yeah, Angela. Huh? Why flip the sign here? Yeah. So one quick answer is sort of what I was telling Matt, is that this way you can think of this as the coefficients of the divisor of a meromorphic function, right? I can think of a map to P1 as being a meromorphic function, and then a very natural object in algebraic geometry is the divisor of a function, which is the collection of zeros and poles weighted with their multiplicity. And so this is the list of coefficients of the divisor. So that's one way. So in a sense, this is a more natural connection to the double ramification cycle theory, the Picard theory that is also lurking in the background here. But I'll give you a second motivation in a couple of minutes once I will tell you a little bit more about the structure of these numbers. Any other question? Yeah. Yes, exactly. Yeah. Also because it rhymes with trouble. No, just kidding. All right. So, in fact, I would say that double Hurwitz numbers are not trouble at all. In fact, they're great, right? So, Golden, Jackson, and Vakil. Right? So this is one algebraic geometer and two combinatorialists that walked into a bar, right? They actually wrote a really great paper where they started studying, it was called Towards the Enumerative Geometry of Double Hurwitz Numbers. And so they think of, okay, well, you should really think of these double Hurwitz numbers as a function, right? It's a function from a parameter space, let me say h inside z to the n, right? So this is where the x lives, like a hyperplane inside z to the n. Maybe I should say z minus 0 to the n. I don't want any of the entries to be 0 because that doesn't have geometric meaning. But it's a hyperplane inside this lattice into Q, right, that for every x produces the number hg of x. And what they show is that hgx is a piecewise polynomial function in the xi's. Okay. And they actually compute the degree to be equal to 4g minus 3 plus n. And in fact, they also observe that there is something I'm gonna abbreviate as a lower degree of 2g minus 3 plus n. And by this is just a horrible way to say that any monomial degree less than 2g minus 3 plus n has coefficient 0. So it's not going to appear in this polynomial. And then they prove that this polynomial is either even or odd. Of course, depending on the parity of 4g minus 3 plus n. Okay, so somehow these numbers that arise from geometry or from Picard theory or from representation theory of the symmetric group, that there's no reason why they should have this sort of polynomial structure, have sort of an interesting, rich structure. Okay, and then what was shown later by Shapiro, Shadrin, and Weinstein. Weinstein, I think that's right, in genus 0. And by myself, Paul Johnson, and Hannah, Mark Fick, in arbitrary genus, is that you can describe kind of wall-crossing formulas for double Hurwitz numbers, which means that, what does it mean for this function to be a piecewise polynomial is that inside H there is a hyperplane arrangement that subdivides, such that the complement of this hyperplane arrangement has a bunch of connected components called chambers. In each chamber, the double Hurwitz number is piecewise polynomial. And then when you go from one chamber to another chamber, the piecewise polynomial changes. And a wall-crossing formula is sort of like the difference, the variation of the two piecewise polynomials on either side of a wall. Okay? And so the second answer to your question, Angela, is that what we observed is that actually if you cross some hyperplane, some coordinate hyperplane, that would be a wall, so that actually corresponds to having some 0 becoming a pole. These actually satisfy the same kind of wall-crossing formula as those that were observed earlier by Gould and Jackson-Vakil that thought of like the two, length of eta 1 and length of 2 as these discrete invariants to be fixed. And so, why having more discrete invariant than needed if, really the discrete invariant that matters is the total length of eta 1 and eta 2 and not actually individual lengths. That's another reason. Okay, so right now I haven't told you anything about double Hurwitz number other than the notation and a bunch of cool facts about them that were found in the literature. And I'm still not going to tell you anything for a while, but at some point here, right? Hannah was walking the world as a young postdoc, right? And like Hannah often does, she sees something beautiful and she says, "I want to make it tropical," right? Yeah. So be careful when you're around Hannah. And so, what's the perspective that Hannah took back then is say, okay, well, if a Hurwitz number is the degree of a tautological morphism of particular moduli spaces, let's see if we can repeat this setup in the tropical world, right? So let me introduce the notion of, yeah. What?
Why is 2 points special?
Well, so the 5-second answer is that 2 points corresponds to basically understanding the multiplication in the class algebra of the symmetric group, but only by the class of a transposition. And so basically you don't need to understand the full multiplication in the class algebra of the symmetric group, but you just, huh?
It's special because it's simple.
Well, it has more structure. Well, yeah, which might be taken to be a synonym, right? It's simpler, but it also has a structure that, like, if you do the full multiplication, you lose, triple Hurwitz numbers are in no way or sense polynomial, or they don't have any of these properties. Yeah. I mean, another reason why you would consider, you might say that this is special again is that this is the thing that makes contact with the theory of neuromorphic functions, with Picard theory, with Jacobian stuff, and so on and so forth, right? Because you have one rational function, a profile of 0, and a profile of poles. Okay, so there's a couple of reasons. Yeah. Cool. So if we want to make this tropical, right, then again, you kind of want to replace all of your geometric objects by sort of piecewise linear analogs, right? So back in the day, and I said, okay, well, a line with P1 with two special points should really be replaced by a line like a copy of R, right? And a curve of genus G should be replaced by a tropical curve. Actually, sorry. Some sort of tropical curve. Right? And a cover should be replaced by a map F, which is piecewise linear in the sense that it is, if you parameterize the length of these tropical curves and you restrict the function to each of the edges, then it's linear in a function on each edge with integer slope. Okay? And so this is a piecewise continuous PL function with integer slope on each edge. Okay? And then again, this datum, like Hannah did yesterday, right? She drew one beautiful, complicated picture that had the source curve and the map and the image and so on and so forth. But then you get tired and bored of having to keep all of this information all spread out. You try to find some way to kind of encode it a little bit more efficiently, right? And yesterday it was just about, well, just keep track of the image and then you can recover anything else. Here you can't quite do that because the image gets all squished, right, to a line. But what you can do is you can just sort of like draw your curve over the image and decorate this picture with some discrete data that keeps track of kind of the slopes of f, right? So for example, if I restrict my f on this top edge, it might have slope 3, so I'm going to put a 3 here, right? And maybe I'm going to put a 2 here, and then maybe I'm going to come up with a 5 and a 1 here. And then, what happens, right, is that when you have a vertex, you want to satisfy a balancing condition, right, which is that the sum of the incoming slopes is the same as the sum of the outgoing slopes. Right? And so maybe I will decorate this. 3 and 2 is 5, and 5 and 1 is 6, so that's bad. So 4 and 1. But then, let's see, can I make this happen? I can make this into, I can still do this as a 2 and a 3. For example. So this is an example of a tropical cover, right? This picture contains all the information that the map contains, right? So long as, of course, as I also know kind of what points of P1s these are. Because, for example, now you can, if you know what this length is here, this L, then you can also figure out what the length of the edges above it are. Right? So this edge should have length. Let me draw it in blue. L over 2, and this should have L over 3. Right? Because 3 times L over 3 is L. Okay. So these are tropical covers, and then again you can say, oh, yeah, question, Monty. Yeah, because the way that you should think of this 2 and this 3 is that basically if you restrict your function just to this edge, and you think you've parameterized this edge, this has a coordinate x, and this one with a coordinate y, then the function is really y equals 2x. And if the image of a particular segment via the function y equals 2x has length L, then yeah. Cool. All right, so like we like to do in this whole school, like, right, if a geometric object walks up to you, you say, well, don't sit alone, but go and have fun with all your kin, right? Get into a moduli space, right? So you can study at the same time the moduli space of all tropical covers, and maybe you fix the discrete invariants, such as the genus of the tropical curve, right? Which, like Hannah was telling you yesterday, is the sum of the Betti number of the graph plus the sum of the genus function at vertices, which in this case I've chosen to be, if I don't write anything, it's going to be 0, right? So this is a tropical cover from a genus 1 curve to a line, degree 5, right? How do you get the degree? You take any point downstairs, you look at the inverse images, and you look at the slopes of the inverse images, add them all up, and this balancing condition is what makes the degree being a well-defined notion. And then with further discrete invariant, like ramification, 3, 2 over minus infinity, and 4, 1 over plus infinity. Right? And if you really want to be sort of very cute and very parallel to the way that we set things up here, you would say that you choose by convention all unbounded edges to be oriented inward, so towards the graph, and then you flip the degrees here, and by flipping means that you should also reverse the order of the edges, and okay, whatever. It's cuteness that is borderline annoying, right? Okay. Okay, but so we have moduli spaces, and again, let's observe for a second that these moduli spaces are abstract cone complexes, right? In the sense that if you fix the topological type of some covers, so for example, in this case, I am fixing the topological type where I have a genus 1 graph with 2 4-valent vertices, labels, A, B on one side, C and D on the other. Right. And this gives rise to a 2-dimensional cone in M14 trop, where sort of the coordinates x and y are the lengths of these edges. These are lengths. And I understand it can be annoying or confusing or both, that there's 2 things that we decorate the edges with, right? Sometimes it's a slope, sometimes it's a length. So if you're ever confused, please ask, right? So what I'm saying right here is that I start by saying, okay, if I just think of abstract tropical curves of this topological type, I can choose the length of these 2 edges independently, and I get a 2-dimensional cone worth of these curves. Right? But if I want to restrict to curves of that topological type that admit a tropical cover of degree 5 with 3 and 2 and 4 and minus 1 and 3 and 2 here, then I have a constraint I have a constraint that, 3 times this length is equal to 2 times this length. Right? So what I'm really doing is I'm cutting a ray of slope 2, 3. Right? And this is a ray of all tropical covers of topological type given by asterisk. Okay, yeah. What?
You said M1 for the crop. Does that mean you're marking? Oh wait, no, 4.
I have 1, 2, 3, 4 marked ends and genus 1. Yeah, yeah. Yeah. Cool. Okay. And then again, you play the same game that Hannah was talking about yesterday in 2-dimension, right? That you start with a bunch of abstract cones, and then you say, well, I'm going to glue them together when, when it happens that when I specialize some edge length to 0, I get a topological type corresponding to some other cone, and then I put that cone in as a face, and so on and so forth, right? So for example, here the silly example is that I can take this cover, right? And this corresponds to just 1 point. And this point is going to become the vertex of this cone, right? So this is okay. Okay. And there's one thing I'm shoving under the rug that maybe I'm just getting caught at, but there's one notion. So when you define a moduli space, it's always, the objects are always isomorphism classes, right? And I haven't told you what the isomorphism are, but from the picture I've drawn, maybe that has come across. And is that what you wanted to ask? No? Okay, so let me finish this thought and then I'll come to your question, right? So, obviously a map like this, there's really not only one because, well, it depends where in R this goes. But I'm going to define 2 covers to be isomorphic if they differ by a translation, like post-composition with translation of R, right? So then this is really, there's only one isomorphism class here, and there's really a 1-dimensional cone. Again, even here as well, right, you could see that if I don't make this, I have one length to choose, and I have one starting point, right? So I have 2-dimensional object. But if I make them all equivalent, I may as well assume that this point is my favorite point, like 37, right? And it's just 1 dimension. Okay. Did you have a question?
So, why don't you choose L as a parameter space and instead use it?
You can, yeah. Yeah, you absolutely can. Yeah. I don't know if there's a really strong motivation to choose one or the other. One reason to choose to do it this way is that then you can, well, let me add one more thing and come back to your question. So these are not just random cones. These are cones with a lattice inside here. And one way to get a lattice here is to induce the lattice from the integral lattice of mgn trop. Right, so for example, 1, 2, 3, so here we go. Right, I have a bunch of points here. And you will notice that if you induce the lattice using, Alessia's proposal, you'll get a different lattice on this ray. And so you can develop formulas in either case, and there will be slightly different linear algebra formula. And I don't know if it's just a historical thing, or Hannah, maybe you can comment on that. Is there a reason to prefer inducing the lattice from MGN trop as opposed from the base space? Or is just kind of what happened historically? And I remember that we had like discussions on this.
I think in a sense you can do this history.
It's a history.
On the plane curves.
Yeah.
You don't have a base.
Yeah. Yeah, so what Hannah is saying is that it's mostly a historical reasons, because this, even though the target space, the one-dimensional target space is in a sense simpler than two-dimensional, the two-dimensional came first, right? And so that was the more natural perspective when you did the target space, the table maps for plane.
Geometrically, there's a motivation. We'll see it next
In the logarithm. I mean, there's a motivation in the sense that they represent different things, right? But
yeah, so because we typically take nodal curves to be reduced,
Mhm.
you're forced to take this.
to take this structure. I see. Okay, cool. That's a good answer. And now I forgot what I was going to say next, but let me regroup for a second. So, yeah. Cool. So we have, I think where we are, right, is that we've constructed a moduli space of tropical covers. So let me call it Herv trop, right, of G to 0, degree, well, let me just say G, and then X, right, because this is parallel to the moduli space for double Hurwitz numbers, right? And this thing is a cone complex where each cone has an integral lattice inside. Right? So they're not just things that are abstractly isomorphic to positive orthons. You have actually picked an isomorphism. Right? And then you can identify the integral points. Okay, and then, just like in the classical case, you can devise a branch morphism. Right? Because what you can do if I draw a picture like this is you can erase the top and you can just remember the positions of your images of the vertices. Okay? And you might want to weight the branching based on the genus and the valence of the vertices, right? So, for example, why? Because somehow you want the number of branch points to remain the same, right? And so this picture, I can think of it as a specialization of this picture, where this length has shrunk to 0, and this one also has gone to 0. Whereas I cannot further make this picture more generic. I cannot create more vertices than this, right? So the most degenerate graphs, which is the most generic covers, are, I learned in the school, cubic graphs by somebody, and trivalent graphs in my world, right? And so if you want to know what is the total number of ramification that a cover should have, you should look at trivalent graphs, and then you say, okay, well, for this particular discrete invariance, I should have 4 branch points corresponding to simple ramification points. And so this point, I think of it as the coincidence of 2 simple branch points, two simple ramification points. So in a branch morphism, they should have weight 2 and they should have weight 2. Okay? So at this point, this is either clear or I can't make it clear in 1 minute, but luckily for you, I made an exercise on the notes that you can, have fun with in the afternoon. But the punchline is that we have a Britrop to some space, right, that we can actually, this is actually, one single cone. And again, part of the exercise to figure out why that is one single cone. But in particular, this is a map of equidimensional cone complexes. Or it's kind of the bottom thing is a cone complex in a silly way because it's one single cone, right? So it's not very exciting. And so we can define the degree I think probably Hannah is going to define this today. Is that the degree of a... So let me... Or maybe next time. But let me preview that. Tropical geometers have been... and convex geometers before tropical geometers and lattice people and toric people, right? They see something like this, and it's like, well, the right notion of degree is not just take a point here and look at the number of inverse images. But if you take a point here in the interior of this cone, and you look at the inverse images, look at the cones that these inverse images belong to, and then you want to see how what the map does to the integral structures. Right, so let me draw a picture so what I say might hopefully... All right. Let me leave Vance here. And what is Vance thinking right now? Okay, what Vance is thinking right now is that you start with a cone down here. Right, this cone has an integral structure. Right? And what you do is you've picked a point in this cone, and you say, what are the cones that map here? And you might have different cones that map here, but each of these cones has its own integral structure. And so on and so forth. And because this map BR is an affine linear Z integral map, right? The map of this lattice is going to be a sublattice. I don't know. Now I'm kind of losing. Oops. It's going to be a sublattice of the lattice here, right? And so you say that this cone covers this cone with a local degree, which is equal to the lattice index of the red lattice, which is the image of the lattice upstairs, inside of the integral lattice downstairs. Right? So this is the sum for all sigma mapping to the one single cone. Actually, let me say open cones mapping to the single cone of the local degree of sigma circ. And so this local degree is the lattice index of the image of sigma dot inside the one single cone. I mean, not right. So I write some formulas, I'll probably get it wrong, and I'll make it more confusing. But yeah, I'm happy to repeat it. Yeah.
So you wrote sigma cert mapping to the one cone. Is this just do all sigmas show up in the sum in the first complex?
So not, let me think so there's a quick answer, which is me cheating, which is like, well, not all sigma, because, if I take the interior of this one single cone, then only top dimensional cones are going to show up, and that's all that matters. Now I'm having a brain moment, but I think all top dimensional cones in our moduli space of covers appear, because it's, they all show up. Yeah, I suppose, I wrote this in a way that would generalize to a situation where instead of one single cone here, you actually have another fan or some sort of locally fan-like thing, and then you probably need to put some extra, those local fans being balanced so that the degree is well defined. And but in this case, it's actually rather simple. Yeah.
Two dimension is going to be different. So we will study this case of ND0 crop, and there we will also have this picture of a tropical variation morphism, which is going to be such a map of core complexes as Renzo describes, and those determinants that I wrote down to end with last time will show up as such lattice indices, right? But there it's not the case that all cones meet a certain cone. Even also in the image, the cone structure is more complicated.
And also the ADM compactification.
Yeah, that's hold your horses. Yeah.
So the automorphisms play no role in this degree?
They do. I'm cheating. Yeah. So I guess the local degree is the lattice index. So each cone is probably weighted by the automorphisms of the cover. Yeah. But automorphisms really need to respect all structures. So for example, this thing does not have any automorphisms because the fact that you have different slopes means you cannot flip that. And these two ends do not, again, they have different slopes, but even if they had the same slopes, we're going to probably want to mark them, right? So there's always some annoying thing that has to be figured out with automorphisms. Yeah, thanks. Okay. So we have now a natural,
Can you say something about how to compute the weights of the
Yes. That's exactly where I'm going, right? So the sentence I was saying is like we have a geometrically natural way to define a tropical Hurwitz number, but you would actually never want to compute it this way, right? It can be done, but computing this lattice index is about computing the determinant of some matrix. Matrices become bigger and bigger, and so, either you're Hannah and she does it while she's having breakfast before tea, right? Or you're anybody else in the world and you don't want to do it, right? And so you kind of try to figure out does this thing, which has again a very natural definition from a tropical geometric point of view, but does it give rise to something which is combinatorially appealing and some combinatorial thing that can be useful, right? And so, again, I think I'm almost out of time today, so I will let me just finish today with an example, and then next time I will say things more generally, right? So this definition, the definition of tropical Hurwitz numbers, gives rise to two things. one thing is a combinatorial algorithm to compute tropical Hurwitz numbers. And the second thing is gives rise to a correspondence theorem with, algebraic double Hurwitz numbers. Okay, so these are sort of two desirable things, right? So let me finish today with just giving one example of this combinatorial algorithm, show through this example that it satisfies this correspondence theorem, and then next time I'll actually describe completely the algorithm and start talking about why this correspondence theorem is true, right? So let's go back. So if you remember, we had kind of a fun example of a double Hurwitz number, which was this. And we even had like its disconnected counterpart. Four and a half. Okay. So these are Hurwitz numbers that you can compute fairly easily with the symmetric group definition, right? Because this 4 transposition has 3, yada yada yada. But let's see how we're gonna recover them tropically. So what I would do is I would start with drawing two strings, 2, 1, and 2, 1, right? And remember I've suppressed it here, but in our notation this r was equal to 2. This is telling me that I have 2 trivalent vertices that I need to put in that thing, and I need to get a tropical cover, right? So what are my options? Well, I have the option of I can either join and then open, and if I do that, then this becomes a 3, okay? Or I can open the 2 into a 1, 1, and then glue the 1 to become a 2. Okay. Or I can open the 2 with a 1, 1, and then so these are the 3 pictures that I can draw, right? Corresponding to tropical covers with this invariance, right? And this picture is disconnected, so I'm probably liking this one for this, but I'm going to exclude it from this. Whereas for this one, I want to keep all 3 of them. And then the way, I'm going to count each of these graphs with a multiplicity, which will, is hiding, it's what if you do this lattice index computation carefully, and then you see, oh, look, this can actually be expressed in this more natural way. And this multiplicity is the product of the weights of the compact, the weights of the compact edges divided by the number of automorphisms of the graph. Matt was pointing out, right? So this picture will contribute with weight 3. This one will contribute with weight 1. And this one will contribute with weights 1 times 1 divided by 2, because here I have an order 2 automorphism of this We wrote a paper and we called this thing a wiener. I don't know. We were young. Huh? Oh, that was Han and I. If Drew had been part of the team, it probably would have been even worse. So, right? But anyway, so you can flip the wiener or the sausage lingo, whatever you want, right? And so you can see that this 4 is this 3 plus 1, and this 4.5 is 3 plus 1 plus 1/2. Okay, so this is at the end how this definition unpacks. Okay, so next time I'll say a little bit more about, what's the general statement for this combinatorial algorithm, some reasons why the correspondence is true, and how this combinatorial algorithm actually is really useful to prove something like piecewise polynomiality and wall crossings. And I now have -2 minutes, so I'll stop here unless there are questions.